Hi, my name is Jim, and our purpose today is to understand a little bit about maximum power transfer. I'm going to start out with a very non-electronic example just to kind of see where we want to be going with this. And what we have here is, say, a baseball game for children perhaps 7 or 8 years old. And oftentimes you'll hear the coach tell them to choke up on the bat. Now the objective here is to hit the ball as far as possible. And that requires two things. First, the highest bat speed possible, and second is they hit the ball in the right place, which would be kind of near the end of the bat. So if a little child is holding the bat far back by the end of it, it's difficult for them to swing it because they don't have all the strength of a grown-up. If they hold it too far up here, it's just kind of like a little stick sticking out. They can wiggle back and forth. But there's a sweet spot, and there's only one sweet spot where for a child's skeletal, muscular body, they can get the maximum bat speed. So basically what we're doing is we are matching the child's physical condition to the bat. And under that circumstance, assuming that they end up hitting the ball kind of near the end of the bat, and directly at no angle here, so there's no pop-ups or grounders, is that the ball will go as far as it can, given the strength of the child. So in electronics we have a similar arrangement. In the matching here, as we see a little circuit here, I've drawn this as an AC source for the time being, but it does not matter. And we have an internal resistance of the source, and sometimes I call that RS, and sometimes in here I'll call it R internal. And the maximum power transfer comes when the load resistance is equal to the internal resistance. Now, AC circuits is similar, except for a few details that we're not going to discuss at this time, of course. So the objective here is to have these two resistors equal. Now, what you have to remember here is that all sources, whether they're voltage sources or current sources, real sources have internal resistance. Some degree of it. Only perfect sources do not. So we're going to start by varying RL, and here we have our DC voltage source here. Let me just make this clear real quick. Show a little battery there. And what we're going to do is adjust the load resistance here, while the internal resistance of the source may or may not be adjustable. Like for a battery, it certainly is not. As a matter of fact, as the battery ages, we might say that the internal resistance goes up. But as we adjust this, and what we can see here, if we start out, and this is a symbol for an adjustable resistor here, potentiometer wired as a rheostat, is what we find when the load resistance is 0 ohms is that there's no power dissipated in it, which would make sense. And as we increase that resistance, what we see is that the power will increase, and then it'll hit a maximum point. And then after that, further increasing it will cause the power to drop and asymptotically approach 0 watts. So no matter how large it is, theoretically it never gets to be 0. So we have a peak power, and this peak power occurs when the load resistance is equal to the internal resistance of the source. Now, if we do this 0 ohm to start with here, it's very nice if we're on the bench and we do it, but with a real piece of equipment, that can be very bad, because that means basically that the output is short-circuited and all the power is dissipated by our internal. So depending upon the piece of equipment, is you can kind of destroy it if you do something like have a load resistor too low or equal to 0 ohms. Now to take a look at this and try to get a handle on what's going on here, if we start out with the load resistor being 0 ohms, is what we would have here in red is 0 volts. And under that circumstances, the current would be limited only by the internal resistance of the source. So we have a maximum current here. Now as we start to increase the load resistance is what we see now as the voltage drop across it starts to rise and asymptotically approaches the source voltage. Now, that does not mean that the power is increasing, it's just the voltage. For example, if we went back to the other page, and let me do that for clarity, if this were 1K and this were 1,000,000 ohms, obviously, using voltage divider, we can see that most of the source voltage, V sub S, would be dropped across the load. So what we get is kind of an inverse relationship between the current and the voltage, and if we multiply these two together, P equals V times I, is what we would see in dotted green is a power transfer curve. And although I probably don't have this centered correctly, do note that the maximum power occurs here, and that'll be the point when the load resistance is equal to the source resistance. Now, down here, I'm not going to cover this, but to actually find out why that's true, it's a relatively simple matter using calculus to do it, and it wouldn't be productive, I don't think, at this time to go through it. But anyway, if we just take a look at one little piece here, is what we see is the instantaneous slope at the peak is equal to 0, and that's going to be rise over run. Now, from the equation I had on the other page, if we take its derivative, and the derivative tells us the rate of change, and set that equal to 0, and solve the equation of the derivative, what we end up with is this guy. Rs equals, the source resistance equals the load resistance. So it's proven mathematically, of course, that that is in fact the case. Now, here's an example where matching is good. And the example I'm going to use here, say, is a taxi cab based transmitter. Oh, I don't know, typically running 200, 250 watts, and the purpose for the dispatchers to be able to talk to the cabs and give them assignments and so forth of where to pick people up. Now, this transmitter, and this is shown as an AC source, but that's okay, just go with it, the context is still the same, is it connects to an antenna, and this is a symbol of an antenna. Now, if the antenna is tuned correctly, what it looks like is a load resistor. And that may seem kind of strange that a wire sticking up in the air can look like a resistor, but the fact is when you have electrons shuffling back and forth on a piece of wire, they tend to radiate signals, energy. That energy has to come from somewhere. So we're just going to pretend here that our antenna is a load resistance, and what our desire would be is to maximize the power that's being created by the source, which is a collection of transistors and tuning coils and capacitors and whatever, to the load, so that the power reaching the antenna is the greatest, so the range from the base station is the greatest. Now, that's a very good example where matching is a good thing. We want to get the maximum power into the load. And the same is true with, say, radio stations. Radio stations, say WTAM, runs a 50,000 watt unmodulated carrier, and the more power they can get within FCC limits means a larger broadcast area, which means more people can listen to it, which means more advertising dollars. So a place where matching is bad, and I want to give you both sides of this, would be in the stereo power amplifiers, and typically they are designed to work with a 4-ohm speaker. So here we have our circuit again, and this here block would represent the amplifiers, the transistors and resistors and associated stuff is being simplified into this, and that's quite okay. And here we have a 4-ohm speaker, and that's my thought of a speaker cone right there. Not a very good artist. But suppose that we have a match here, is that the internal resistance is 4 ohms. So we'd think that that'd be ideal. I used to think that. But suppose we have a drum strike, and this is going to be a transient coming off of a drum strike, and the actual signal is in blue. Now, the speaker cone has mass, so it's not going to follow the electrical signal exactly, and when it reaches where it should be stopping, well, you have inertia. It's moving, and it can't stop that fast. So basically, it rings and eventually comes to the place where it should be, in spatial respect to the driving signal. Now, this little guy up here where this cone is kind of going back and forth where it shouldn't be has a muddiness to the sound, and that's called distortion. So that's not a good thing if we were to match that. And in fact, the internal resistance of this, and this is to mitigate this, is not 4 ohms. It's much less. And if you want to find out what it is, I'm not getting into a lot of detail here, is in your amplifier specifications, you would look up the damping factor. The internal resistance is equal to the load resistance divided by the damping factor. And if we say we have a damping factor of 15, it comes out to be quite low. As a matter of fact, 0.266 repeat ohms. So what happens now is that here's our electrical signal again in black. Here's the speaker cone in blue, accelerates, gets to the top. Now, as the cone continues to move, the voice coil in the speaker is cutting a magnetic field. And that is a power source. And that is basically feeding a very low resistance of the amplifier. And like a car, sometimes when you turn on the headlights, you might hear the alternator bell squeak. That is because more mechanical energy is being converted into electrical energy. So the amplifier effectively shorts out the speaker, which is acting as a power source. As you can see, it settles very quickly. Thus, there's much less distortion. And we would say the ringing, which we had those little cycles up there, would be damped. So that's an example where you don't want to match. And suppose you connected a bunch of speakers in parallel that equaled 266.6 repeat milliohms. Theoretically, you'd get a ton more power out of it, but the protection circuit on the amplifier should shut it down. It wasn't designed to deliver that kind of power, and if the protection circuit didn't work, you'd blow up the amplifier. You'd be replacing transistors and possibly power supply components. So, in summary here, there's a time you want to match and a time you do not want to match. Now suppose what we want to do is pick a value of load resistance here that's going to allow maximum power transfer, and this guy here would be the source. So the easiest way to do this is by Thevenin equivalent circuit, although you could use series parallel analysis. So to do that, and this is just kind of a little review of Thevenin, and obviously you'd have to have studied Thevenin to be able to do maximum power transfer for this example, is we remove the load resistor, and what we want to do is find the open circuit, sometimes referred to as VOC, sub-OC rather, also called V-Thevenin voltage. So we unplug that, and now we have to take a look at the current flows. Well, what we can see so far is we have a current flow here, and this is 12 volts. Let me write that down, kind of. Certainly through this path. Well, that's kind of obvious. But since we have nothing connected here, the current flow through these two resistors is 0. What that means is the voltage drop, DROP, across the resistors is equal to 0. Anytime you have a voltage drop equal to 0, means that the voltage on each side of the resistor is the same. There's no drop in the resistor. There's no current flowing through it. So we can now simplify the circuit to simply this. Applying voltage divider is what we see here, is we end up with a VTH equal to 9 volts. Easy enough. Now we have to find RTH, that's the Thevenin equivalent resistance, looking into the source. Now what you have to know here, and this is important, is the internal resistance of our voltage source is going to be 0 ohms, and if it were a current source, the internal resistance is 0 ohms. Now realistically, when we started this, I said that all sources have internal resistance. However, suppose that this is a car battery with an internal resistance which is incredibly low. Well, relative to our circuit values here, we can eliminate that from the calculation. And a lot of batteries or cells, like lithium-ion cell is fully charged, that is in fact the case. So we're going to replace this here with its internal resistance of a voltage source is going to be 0 ohms, a short circuit, and with a current source, it's going to be an open circuit. Remember this. That's key to a lot of things coming up in the future. Now all we have to do then is take a look at this, and what we can see is that the 1K and the 3K resistor are in parallel. How do we define a parallel circuit? Is that when two sides of a component are connected to two sides of another component. In a series circuit, like say for example this, what we see is one side of the 1.5K resistor is connected to one side of the 1.K and one side of the 3K. So these two resistors are in fact in parallel, and you need to kind of see that this lead of the resistor goes around and meets him. So what I'm going to do for that is to redraw it a little bit and actually show it in a normal form for a parallel circuit. Anytime you run into problems analyzing this sort of stuff, if you can redraw it, it gives you insight on how to solve it. That's a good idea. So what we see here is we have 1K in parallel with 3K, and then what we want to do here is find out what the equivalent resistance of these two guys are, and then they'll be in series with the 4K and the 1.5K. So doing that, RTH is going to be equal to, in parentheses, 3K in parallel with 1K, that's the shorthand abbreviation, plus 1.5K plus the 4K. So first we'll calculate what the parallel resistance is using product over sum. That's easy enough. 3K times 1K divided by 3K plus 1K gives 3/4 K equals 0.75K equals 750 ohms. Next thing, redrew it again just for clarity, leaving no steps kind of missing here that you have to guess about. RTH looking in here, as you can see, is a series combination of these three resistors, and if we add them together, what we get is RTH value of 6.25K. So that would be the load that we would need to connect to get maximum power transfer, and then this is what our circuit would look like. So in this here, I'm replacing the source with VTH, 9 volts, and the internal resistance was 6.25K, and then the load resistance, 6.25K. And if I want to find the parameters of the circuit's voltage, current, power that's being dissipated by the load, very simple. Voltage across the load is simply equal to VTH divided by 2. Why 2? Resistors are equal. And that's going to be equal to 4.5 volts. What's the current flow? Well, that's the voltage divided by the resistance, and that would be 720 microamperes. Power dissipated in the load, well, we have three choices here. V squared over R, I squared times R, and V times I. You must know the three power equations. I've chosen to solve this V squared over R, and that gives us 3.24 milliwatts. Now, what if the source were a current? What if our source were a current source? What we can do by Norton, and this is what it would look like, by the way. Its internal resistance would be in parallel with the current source. Is using Norton's equivalent circuit, is we could convert this into a voltage source where R is equal to R. And then we can solve it. Now you can also solve it directly with a current source, except looking in, you replace this with an open circuit. So that's the thought of this, and going back a little bit here, my closing comment is realistically, we may have a fixed load here. One more page. This may be fixed, and this would have to be adjusted. So in that case, we know what RL is, and then what we would do would be to Thevenize this here, and it would be really straightforward to do that because our source, VTH, which we don't know what it is yet, and let us say the load here is 1K, is going to end up being 1K, and this would be our 1K load. So this stuff has to be converted into 1K. All we got to do is get a resistor out of the drawer to do it. It's proper power. The question is what is VTH? So you might have to do an AC analysis on this, or looking into this, find VTH to do that. So two options: change the load resistor, change the source resistor to get maximum power transfer. Well, that's about it. I conclude, and thank you for watching.